Hi guys, welcome to a new video. We have this problem and we want to talk about it. The problem says the electric potential at a perpendicular distance r from a long straight wire of cross-sectional radius is given by the following expression. V is equal to minus k log of r dividing a, where k is a constant. We want to calculate the electric field as a function of distance. Hence, using Gauss theorem, we want to determine the charge Q per unit length of the wire. A second identical wire carrying charge minus Q per unit length is placed parallel to the first at a distance d from it. We want to calculate the potential difference between the wires, assuming that d is much higher than a. Okay guys, let's solve this problem. So for the solution of this problem, we can say that as a general rule, the relationship between the electric field and the potential V is given by the following expression. E is equal to minus gradient of V. However, in this case, the field due to the wire clearly has cylindrical symmetry, and we will see that in a little bit, but for now we can assume that the field is cylindrical. It has cylindrical symmetry. So we can write something like this. E is equal to minus derivative of the potential with respect to the radius. Differentiating the expression for B, we will have something like this. According to the problem, we have that the potential electric is given by the expression like minus K log of R dividing A. So we want to differentiate this expression. We will have something like E is equal to, let's call this equation number 2, minus dV dr. This is equal, so I will put the potential electric right here into this equation. I will have minus, okay, derivative with respect to the R of the potential electric, and the potential electric is minus K log of R dividing A. So I will do some algebra right here. I will take this, okay, we know this K is constant, is a constant, right? And so it will go out of the derivative. So we will have something like minus, okay, I open parentheses, minus, okay, K, I taking K out of the derivative because it's a constant, and I write derivative with respect to the radius of log of R dividing A, right? Then we will have something like E is equal, so we know minus and minus is plus right here, K. Okay, I need to do something. Derivative with respect to the radius of the log of A, right? Log of R dividing A. But if I use the log relationship of the division of two terms, this is going to be something like log of r minus log of a, right? So those are the properties of logarithms. That is equal to k. Okay. So derivative with respect r of log of r is 1 dividing r multiplying the derivative of the function of the argument of the logarithms, and this is dr, right? Minus 1 dividing a dr. Derivative properties for the log function right here. Well, this is 0 because a doesn't depend of r, and this dividing this is 1, so e is going to be something like e is equal to k dividing r. I will call this equation number 3. Okay guys, now I will use the Gauss theorem. As we know, the Gauss theorem states that for a closed region of space, the integral of the electric field dot ds is equal to the summation of the charges inside the Gaussian surface dividing the electrical permeability in the vacuum. Okay, so here we have E. E is the electric field vector on the surface of the region. We have ds as an element of the vector area surface, and this is pointing outwards, and we have the summation of the charges as the total charge contained within the region of space. Now we want to choose a cylindrical region of space coaxial with the wire and having radius r and length L. So I will have an illustration for this situation right now. Okay, here we have the illustration. It's clear that over the curved surface, the magnitude of E is constant and it is directed everywhere perpendicular to the surface. So here basically we have the illustration right here, right? And this is the wire that is charged with charge Q, and I draw the Gaussian surface, right? And we have the radius r of the Gaussian surface right here. We have the length L of the Gaussian surface, all right? And I draw an element of area right here. So as we said, the electric field, let me talk about it real fast. The electric field is perpendicular. Remember that at the beginning of the problem we said that the electric field is perpendicular to the Gaussian surface, right? And it has cylindrical symmetry. Do you remember that? Okay, here that's what's happening. The electric field is pointing outwards of the wire, and it has symmetry. It's easy to see, right? Right here I draw an element of area of the Gaussian surface, and as you can see, the distance between the center and the surface is r. it covers an angle d theta, right? So it's d theta and not theta because this is differential element of surface. So its dimensions are all of its dimensions have differential magnitudes. You know what I mean? It's like this is a differential section. All the dimensions are differentials, right? So right here we have the length of arch of this little cone, and its length is r d theta, right? Because the length of the arc is the distance of the radius multiplying the angle, right? And here we have the element dl. So basically the vector ds has our radial direction and is pointing outwards of the surface. Its direction makes angle of 90 degrees with respect to the surface. All right, so now we can write the following. We can write the integral of E point ds or E dot ds is equal to integral. Okay, we know that the electric field has radial direction or cylindrical symmetry, so we can write the electric field like E, magnitude E, and direction R. Okay, dot ds, but ds is the ds, as you can see, is the product of its dimensions. So is r d theta is r d theta dl pointing on the radial direction. Okay, so we can write E dot ds as er r d theta dl pointing to the radial direction, and this is equal to, okay, the terms that don't depend of the differentials here, I can take them out of the integral and I can have E r, so I take this out of the integral, I take this r and I write integral of d theta and the integral of dl. So, and I do the dot product of this r with this dot with this r, like r dot r, right? The limits of these integrals are, you know, theta, it goes all the way around, it goes from 0 to p. If you see here, theta goes all the way around, and dl goes from 0 to L, and theta goes all the way around. So we write here from 0 to 2p d theta and 0 to L dl. And we will have then the integral of E dot ds is equal to ER. Okay, integral of the theta is theta from 0 to 2p is 2p. Integral of the L from 0 to L is L. And this r dot r is equal to 1 because those vectors, this is the dot product, those vectors, they have magnitude equal to 1 because those are unitary vectors and they are parallel. So 1 multiplying the cosine of 0. So that's 1. Okay. So we have this expression now. Okay. Now we come back to equation number 4. I forgot to say that this is equation number 4, but we can fix it real quick. So I called this equation like the Gauss theorem, equation number 4. And from this equation, we have the integral of d dot ds is equal to the total charge dividing the epsilon 0. Okay, from equation 4, we have the E R 2p L is equal to summation of charges dividing epsilon 0. The summation of charge, we can write it like the total charge dividing epsilon 0, the electrical permittivity of the vacuum. Okay, so where summation of charges is equal to total charge, and that's it. Now, and I can write it like more easy like this, easier. So I can get something like this, like then we have that Q total is equal to E R 2 pi L, this epsilon 0, I send it to the other side of the equation multiplying, and we have this. Remember that from equation 3, we have that from 3, we have that E is equal to K dividing R. Okay, from equation 3. So I replace this equation into this one. I replace equation number 3 into this one, and we have Q total is equal to K dividing R multiplying 2 pi L epsilon 0. These two R's, they cancel each other, and I send this L is multiplying on this side of the equation. I will send it to divide to this side of the equation. Okay, doing that, I will have Q total dividing L equal to 2 pi K epsilon 0. And this is the charge per unit length of the wire. Now we go to the second part of the problem that says we have another wire, but this one has charge minus Q, a negative charge. So if we now include another identical wire carrying charge per unit length minus Q at a distance d from the first one, as is shown here. So we have here the illustration, right? We have the first wire right here with charge Q, and the second wire right here with charge minus Q. The distance between them is the okay, I draw this distance R as the, you know, we could have here the Gaussian surface, right, part of it all the way around the charge, but I only drawing just a little part of it because I don't have enough room here, but this is a part of the Gaussian surface, as we know. Okay, the distance between the charges is d. So what happened now? We want to calculate the electric field or the total field of these two charges by the superposition principle. Why I have this R right here? Okay, because I want to write the electric field like this. Okay, remember that the electric field and the distance r is given by this expression, right? That's why I have this distance r right here, okay? So the electric field and a distance r due to the wire carrying charge per unit length, charge q per unit length, is given by, as we know, E is equal K dividing R, right? For the positive charge here. So, and the field due to the wire carrying charge per unit length minus Q is similarly given by the following expression: E equal K dividing D minus R. This is the field given by the wire, or the field produced by the wire with charge minus Q. Okay, so why this? Okay, let's come back to the illustration. If I have this, point here, okay? The distance between this and this, and between this wire and this point is R. So by definition, the electric field is this. Okay? Similarly, the electric field due to this wire is at this point, and the distance between this point and the wire is D minus R. So I use the same expression, but instead using R, I use D minus R, okay? Because it's the distance between the second wire and the point in consideration that is this one. So that's why I write the expression for the electric field like this. So the total field is the superposition of the two fields, right? So I will write E total like the superposition K dividing R plus K dividing D minus R. All right. I will take the K out of the terms. I write it like this. So the potential difference between the wires is found integrating the field with respect to the radius, with respect to the distance, right? Between A and D minus A. It's because if we go to the problem, we will have a second identical wire carrying charge minus Q per unit length is placed parallel to the first at a distance D from it. Calculate the potential difference between the wires, assuming that D is much higher than A. So we want to calculate the electric field. So we want to calculate the potential difference between the wires, okay? And because we have that D is much higher than A, we use A as the and D minus A as the integration limits. So we will have V is equal to K integral from when R is equal to A from R equal to D minus A of 1 dividing R plus 1 dividing D minus R dr. Okay. The integral of 1 dividing R is log of R, right? So we will have K log of R, natural log, right? Minus natural log of D minus R, with the limits going from A to D minus A. Okay. The following is the result of this K. Okay, this one goes from D minus A to A, and we write log of D minus A minus log of A, right? And now I evaluate the limits on the second part, on the second term. It would be log of D minus, I replace R as D minus A minus log of D minus A, because I replaced R like A right here. This D cancels with this one when I, because this is this D minus A, this D cancels with this one, and we will have something like this. V is equal to K okay, log of D minus A minus log of A. Okay, I will have minus log of, okay, we will have this minus with this minus is plus, okay? So we will have log of A minus log of D minus A. This term, I will disappear this parenthesis, okay? When I do that, this term, the first term becomes negative, and the second term turns positive, and I will have, okay? I will have that. All right. So this adds together with this one, and I will have 2 times this term, and this one adds together with this one, and I will have minus 2 times this term. So we will have the following expression: V is equal to K two times logarithm of D minus A. I prefer to say log instead of logarithm. It's easier and faster. Minus 2 log of A. And then we will have that V is equal to 2K multiplying log of, okay, I apply the properties of the logarithms of properties of log, and right, the subtraction is equal to D minus A dividing A, right? And if D it's much higher than A, because we are varying the distance r as A. Okay, so if D is much higher than A, V can be approximated to the following expression. Okay guys, this is the solution of this problem. Hopefully you like it. Please give me a thumbs up if you like it, and subscribe to my channel. You can share this content with your friends to study, learn some physics with me. Hopefully see you on the next video. Bye.